Hello friends, welcome back to our video lecture series on course titled Fluid Mechanics 2. In this lecture we will continue with our previous topic centrifugal pumps, and we will be solving some numerical which is based on the minimum starting speed of the pump. So just before proceeding, let's see what we have discussed in the last lecture, minimum starting speed, and we have derived the expression for the minimum starting speed, which was given by the expression n minimum is equal to 120 multiplied by manometric efficiency multiplied by VW2 multiplied by D2 divided by pi multiplied by D2 square minus D1 square. This is what the expression what we have derived in the last lecture for the minimum starting speed of the centrifugal pump. Now we will be solving some numerical for the calculation of minimum starting speed. So statement of the first numerical goes like this: a centrifugal pump impeller has a diameter at the inlet and at outlet as 360 mm and 720 mm respectively. So D1 and D2 are given. The flow velocity at inlet is 2.4 meter per second, velocity of flow, and the vanes are set back at an angle of 45 degree at the outlet. So outlet vane angle is given in the numerical. If the manometric efficiency is 70%, manometric efficiency is also given. Calculate the minimum starting speed of the pump. Now we know that minimum starting speed of the pump is given by this expression. So the first thing, we will just sum up all the given data, D1, D2, and velocity of flow. We know that in case of centrifugal pump, whatever our VF1 will always be equal to VF2, velocity of flow at the inlet and at the outlet, both are same. And outlet vane angle, that is phi, which is also given 45 degree, and manometric efficiency is given as 70%. Now what we need to calculate, that is minimum starting speed of the pump, which is given by the expression 120 multiplied by manometric efficiency multiplied by VW2 multiplied by D2 divided by pi multiplied by D2 square minus D1 square. Now if we look at this expression, what we have already this D1 and D2, we already have this D2 in the expression. Manometric efficiency is also given in the numerical. Just we need to calculate this VW2. Now we have discussed in the previous lectures that how to calculate that VW2. So we're gonna use outlet velocity triangle, and just look what you have from the outlet velocity triangle. Now if you look at the outlet velocity triangle, you have this phi. Now by using this phi, you can calculate this VW2. So which angle we're gonna use, because if you have this vertical and if you need to calculate this horizontal, of course we're gonna use tan relationship, that is tan of phi is equal to, that is opposite, that is given by VF2 divided by this length, that is given by the expression this whole, that is U2 minus VW2. So we need to calculate this U2, we need to calculate this VW2 by using this phi, whatever we have. Now while calculating this U2 and VW2, of course we will be need N, because this U cannot be calculated without N, because this U is given by the expression pi D2 N divided by 60. So we are going to replace this N with the minimum speed of the centrifugal pump, that is N minimum. So once you put this N minimum, calculate your U2 or VW2 both in terms of N minimum, and just simply putting that value in our expression of the minimum starting speed, you will be getting the required answer of the minimum starting speed. So first calculate this U2 in terms of N minimum by putting this value of D2 here. What we are getting here, 0.0377 N. Now once we calculate this U2 in terms of N, just simply considering the relationship at the outlet velocity triangle, tan of phi is equal to VF2 divided by U2 minus VW2. Now writing this expression in terms of VW2, what we are getting, VW2 is equal to U2 minus VF2 divided by tan of phi. Even you can remember this expression as it is, because you can directly use this expression for the computation of VW2 in case of centrifugal pumps. So we are getting this VW2 in terms of N minimum, that is 0.0377 N minimum minus 2.4. So simply putting this VW2 in our expression of the minimum starting speed, and just by simply putting those values in this expression and just calculate whatever the N minimum, value of the N minimum, what we are getting here, N minimum is equal to 137.2 rpm. So this is what our required answer. Hope you understood this particular numerical. Let's move to solve another numerical. So the statement of second numerical goes like this. The impeller of centrifugal pump having external and internal diameter 600 mm and 200 mm respectively, this D1 and D2 are given, delivers a discharge of 500 liters per second against the head of 15 meter. So the discharge is given, and this head against which my pump is working is also given in the numerical, that is manometric head, and the pump is running at a speed of 600 rpm. So the value of n is given itself. The velocity of flow through the impeller is constant and equal to 2.0 meter per second, that is Vf1 and Vf2 both are given. The vanes are set back at an angle of 30 degree at the outlet. So outlet vane angle is given, that means that phi is given in the numerical. If the entry to the pump is radial, so of course it is the in case of centrifugal pump our discharge is always radial, and which is also given in the numerical. Calculate power required. They asked to calculate power required, efficiency. So simply whenever they only mention the efficiency, we are simply going to calculate manometric efficiency, as in the case of turbine where we have calculated hydraulic efficiency. When they simply mention the calculate efficiency of the turbine, at the time we have calculated manometric hydraulic efficiency. So whenever in case of pump they asked to calculate efficiency and haven't mentioned anything about the efficiency, then simply calculate manometric efficiency. And minimum starting speed of the pump. So this is the speed which is given for the centrifugal pump at which it is running, but what should be the minimum starting speed for commencing the flow, that they have asked to calculate. We know the expression for it. So just first thing, write down all the given data, and then we will be calculating all the required unknowns one by one. First we will calculate what is the power required. We know that power required is equal to the work done by the impeller on the fluid, and that is given by the expression rho q multiplied by Vw2 multiplied by U2. So for the calculation of power required, we will be required this Q, because as they have given water rho 1000, Vw2, that is we need to calculate, and U2. Now we know that this D1 and D2 given, N is given, then you can calculate U1 and U2 both easily by using expression pi dN upon 60. So for calculation of U1 take D1, and for the calculation of U2 take D2. So both are coming out as 6.28 meter per second and 18.84 meter per second respectively. Once you have a value of U1 and U2, we will be proceeding for the calculation of Vw2. As usual, we will be using this relationship of the tan of phi, because phi is given in the numerical and we are using it for the calculation of this Vw2, which is given by the expression Vw2 is equal to U2 minus Vf2 divided by tan of phi. As I told you, you can also remember this expression for direct use of the Vw2. If you don't want to memorize it, then in that case you can simply go with the trigonometrical relationship whatever you have. So just simply by putting all the values of U2 and Vf2 in this expression of and the phi, then we are getting their V2 as 15.38 meter per second. Discharge is already given in the numerical. So simply taking the putting the value of this density, discharge, Vw2 and U2, we are getting our required power, value of the required power, that is coming out as 144.93 kilowatt. Now next thing, they asked to calculate manometric efficiency, which is given by the expression GHM, that is manometric head, G multiplied by manometric head divided by Vw2 multiplied by U2. Now if you see here, Vw2 already calculated, U2 is also calculated, HM already given in the numerical. Simply putting the values of those unknowns in the expression, we are directly getting the manometric efficiency as 0.50786, that is 50.78%. This is our required answer of the manometric efficiency. And the last thing, they asked to calculate minimum starting speed of the centrifugal pump, which is given by the expression N minimum is equal to 120 multiplied by manometric efficiency multiplied by Vw2 D2 divided by pi D2 square minus D1 square. Everything we already have, that Vw2 we have calculated, D1 and D2 both are given in the numerical, and manometric efficiency just now we have calculated. Just simply putting all those values in this given expression, we are getting our minimum starting speed of the centrifugal pump, that is coming out as 579.38 revolution per minute. In case you forget this particular expression, then even you can go with this expression as well. If you have a value of u1 and u2 and this value of this manometric head, in that case you can simply go with this expression as well. U2 square divided by twice of g minus u1 square divided by twice of g is equal to hm. Just simply putting all the values, that it's this u2 is equal to pi d1n divided by 60, u1 is equal to pi d1 divided d1n divided by 60, and just calculating the value of n from there. You can even go from that particular expression, go through that expression as well. You will be getting the same answer in that case as well. So those are the some numerical which we have solved based on the minimum starting speed of the turbine. Those are the references which I have used while preparing my presentation. Thank you for watching.